As English poet and playwright William Shakespeare once famously quipped, "If calculus be the food of life, then integrate on." And that we shall do. Today, we will be dicing and slicing a very delectable, interesting, and honestly quite spicy integral. And we'll be taking a look here at Sophomore's dream, which, as you can see, is the integral from 0 to 1 of x to the negative x dx. So, without much further ado, let's get straight to this very interesting proof. Okay, so let's first write our integral again. The integral from 0 to 1 of x to the negative x dx. Okay, so to begin, what can we do to start manipulating this? Well, we can say, okay, it's the integral from 0 to 1 of e to the natural log of x to the negative x, still integrating with respect to x. Now, if you recall, if we take e raised to the natural log of something, we just get whatever that's something, right? So it's e to the natural log of x, we just get x, because that is how logarithms work, because remember, natural log is simply log base e. So I've not changed values, so this is valid. And now, if you remember, an interesting property of logarithms is if I have a log of something raised to some power, I can bring that exponent in front of the logarithm. So this will become the natural log. I'll just write it out. This will become the integral from 0 to 1 of e to the negative x times the natural log of x dx. Okay, so we've simplified this a little bit more. But now, let's do something very interesting. If you recall, the Maclaurin series for e to the x is nothing more than the sum from n equals 0. Wait, actually, it was a pretty bad sigma. There you go. The sum from n equals 0 to n equals infinity, right, of x to the n over n factorial. This is simply the definition of the Maclaurin series for e to the x. So in this case, x, right, this here, is actually negative x times the natural log of x. So I can simply plug this in, raise it to the n, and divide by n factorial, right, as I'm taking the sum of this from n equals 0 to n equals infinity. And I'm expressing this, I have not changed the value. So we can say, I have not changed the bounds of integration, still integrating from 0 to 1 with respect to x. Right, now I can say I'm integrating the sum of as n equals 0 to infinity of negative x times the natural log of x, all raised to the n over n factorial, and then again times dx, because we're still integrating with respect to x. And now, just erase this. Now there's something very important. So I know we discussed that we can express e to the x, or e to the negative x times the natural log of x. We can express that as a Maclaurin series. Well, there's an interesting thing about the Maclaurin series called uniform convergence. Because of this, we can take this sum and move it outside the integral to help clean some stuff up. So this will give us now, okay, the sum as n equals 0 to n equals infinity of, well, this n factorial here is just a constant, because remember, we're integrating with respect to x. So this n is a constant. So I could bring it out, and it will not change the value of the integral. Again, we're still integrating from 0 to 1. We're still integrating with respect to x. And now we can say, we brought these two out. So we have negative x times the natural log of x raised to the n. So I can just say, well, this is nothing more than x to the n times the negative natural log of x to the n. I'm just multiplying this out, distributing. This is perfectly legal. So, okay, x to the n times the negative natural log of x to the n, and again, integrating with respect to x. Okay, it is now this point that we should make a substitution. If we let some variable u, this is not mu, right? Don't want to confuse that with Greek letter mu. This is u, there we go, no front tail. Let us declare we have a substitution such that a variable u is the negative natural log of x. Doing this will allow us to say, fine, the derivative of u is going to be negative 1 over x, is a negative natural log, times dx. Okay? But we just have a plain dx, right? We don't have this negative 1 over x coefficient. So we can say, okay, fine, if we want plain dx, multiply by both sides by negative x to get dx equals negative x du. Now we can start plugging some things in for our substitution. So obviously out front, we still have our same good old summation from n equals 0 to n equals infinity, and then of this constant 1 over n factorial. And I'm just going to erase this little thing to give us some more room, right? We have then the integral. Now we have changed our bounds of integration. We've said u is a negative natural log of x. And remember, if this is our x, this is our y, if our function f of x is equal to negative natural log of x, that's just going to be a function that looks like this. Has a vertical asymptote at x equals 0, and it crosses the x-axis, it crosses the x-axis at the point 1 comma 0. So if we look at this graph, well, our lower bound is 0. As this function, this is the negative natural log of x function. As we approach 0, we're going up and up and up and up and up towards infinity. And as we approach 1, that just gives us 0. Okay? So let's make some substitutions. Since we know that u is negative natural log of x, this term right here, the negative natural log of x to the n, simply becomes u to the n. But this x to the n, and remember we have this negative x there, we need to express that in terms of u. So we know from here we have x to the n. We need to multiply by negative x, because in order for the substitution to be valid. Well, if you recall that we multiply functions of the same base, right? We can add their exponents. So this is going to be negative x to the n plus 1. And recall from here, if we've said u is the negative natural log of x, if we multiply both sides by negative 1, right? So negative u equals the natural log, well, the natural log, of x. It's terrible natural log. We raise both sides to the e, and we can then conclude, we can say x is equal to e to the negative u. Based on this definition, we can say that negative x to the n plus 1 is going to give us negative e to the negative u times n plus 1, because we're raising x to the n plus 1, therefore we're raising e to the negative u to the n plus 1, so we can just multiply. So raising it to power, we can just multiply the coefficients and we end up getting this. So we can say, okay, we know that our x to the n times our dx to get us in terms of du is going to be negative e to the negative u times n plus 1. Again, du because we are integrating with respect to u. But now, if you recall, or you maybe notice something, we have this pesky minus sign here, right? It's just kind of nasty. But actually, it's interesting because if we change the bounds, if we flip the bounds of integration, say we go from 0 to infinity instead of vice versa, we have to multiply by a negative 1. But we have a negative 1 right here. And because we know a negative times a negative is a positive, effectively, we can eliminate this minus sign and change the bounds of integration to something we're a little bit more familiar with, 0 to infinity. Okay, so it is at this point that things are starting to look up for us. We've made some progress. We still have some interesting things left to do. At this point, let's clean up this integral. Let us make a substitution s. Let us define a variable s that such that s equals u times n plus 1. Okay? If we differentiate s with respect to u, we're going to get, well, just n plus 1 times du. But like over here, we just have a du by itself. We don't have this n plus 1 term. So, okay, fine. Well, we can say if we want our du to express our du in terms of ds by itself, just simple algebra ds over n plus 1. Okay, so that's something we're going to have to multiply. So we can start kind of getting stuff written out over here. So again, the sum is n equals 0 to n equals infinity. Again, the same concept, 1 over n factorial. Again, I'm taking the integral. Now, well, let's check based on this definition. If my u is 0, well, 0 times anything gives me 0. And infinity times n plus 1, remember n plus n is a constant in this case. So it could be anything, it doesn't matter. Infinity times something is just going to give us, it's just infinity. So there we go. Our bounds of integration actually have not changed, which is interesting and also very helpful. Now, we know that we've defined s as u times n plus 1. We have that, we just need to make it a minus, so we can this part simplify as e to the negative s. Okay, what about this u to the n? Well, we know that if s is u times n plus 1, then u by simple algebra is just going to be s over n plus 1. Okay, so we can say, fine, we're going to be multiplying by this u, which is really s over n plus 1, raised all to the n. And then remember, because we've defined our du in terms of our ds, we have to multiply by this extra coefficient. So times ds over n plus 1. Okay. So now, let's just clean this up a little bit. Clean this up. So, I'm just going to write some stuff over here so I don't have to keep rewriting this whole sum and integral again. So, if we know we have s over n plus 1 raised to the n, that's going to simply give us s to the n over n plus 1 to the n. It's s. This is just simple, simple manipulation, right? Well, I also have, so let's simplify. It's sort of just expressing this term in just a little bit different way. Well, I'm multiplying by this 1 over n plus 1 term here. And if you notice what's interesting is these are the same. Because again, if you have the same base and you're multiplying, you can have your same base, add the exponents. So this is going to give us s to the n, we'll kind of pull off, times 1 over n plus 1 to the n plus 1, because this is n plus 1 to the n times, or 1 over that, 1 over n plus 1 to the n times 1 over n plus 1 raised to the 1, really. So we can multiply them, add their exponents, right? Effectively, we get n plus 1 raised to the n plus 1. Of course, times our s to the n. So now let's pull this guy out to hang out with the factorial, because obviously, remember, n is a constant. We're integrating with respect to s. We'll leave the s to the n because obviously we are integrating with respect to s, so we need him. And we'll start to see a very amazing thing. This is where it really gets exciting. So again, sum from n equals 0 to n equals infinity of 1 over n factorial. And remember, we've pulled out a 1 over n plus 1 to the n plus 1 by our manipulation, which leaves us with this integral from 0 to infinity of e to the negative s times s to the n, and of course we're integrating with respect to s. And now this, my friends, this integral right here, I'm going to just outline it in green so it's easy to see. This integral, this is amazing. Why? Well, let's take a look at the pi function. And if you have never heard of the pi function, well, don't freak out. Fix that. Yep. Pi function. Don't freak out, because there's nothing to be worried about. It's actually really cool, and if you have never heard of it, well, then this is a chance to learn something. It's really, really interesting. So we can define pi of n. Now, if you haven't heard of pi, but you have heard, actually, let me just fix it so it's a little bit neater. There we go. If you haven't heard of pi, but you have heard of or seen this thing, which is gamma. Gamma of n plus 1 is the same thing as pi of n. Pi of n is Gauss's way of explaining it, and personally it's just better because you don't have to deal with n plus 1. But what's cool is this equals the integral from 0 to infinity. And let's say we have a dummy variable s. Okay, our function is in terms of n, so we raise s to the n, and we have to multiply by e to the negative s, and then of course ds, because this is s is our dummy variable. And so notice, because we have an n, we're plugging in an n here. And if you look, this is the exact same integral as this. They are identical. So we've said this integral, this whole integral from 0 to infinity of e to the negative s, s to the n ds, is nothing more than the pi function. And now you might be saying, Oscar, what? The pi function, why do I care? Because the pi function is equal to n factorial. Because pi of n, or gamma of n plus 1, is the integral from 0 to infinity of s to the n e to the negative s ds, which is n factorial, which is crazy. And if you are baffled or curious by this, then I suggest that there's a really great video by Black Pen Red Pen that I recommend you check out, and he explains the beauty of the gamma function and sort of a derivation. But for now, to save time, just accept that this is true. And if you're interested, definitely I encourage you to learn more. It's really interesting derivation, really interesting function. But so if we say that this integral here that we've cleaned up, right? The integral from 0 to infinity of e to the negative s to the n ds. If we said this entire thing is nothing more, this integral is nothing more than n factorial, well, we can cancel something out, as you may have noticed. So if we come here, kind of hitting this light, the sum as n equals 0 to infinity, 1 over n factorial, right? And then we are also multiplying by that 1 over n, n plus 1 to the n plus 1. And then this entire integral has disappeared, has been replaced with the simple n factorial. That, my friends, is the beauty of the pi function. It's just, I mean, this is really, I think, one of those cool things in mathematics, like Euler's identity. It's just so cool because there's a really satisfying feeling when you have this difficult problem, and step by step you're trudging through, you're making substitutions, you're doing algebraic manipulations or trig substitutions, and then you're kind of trying to figure out, well, I'm not sure where this is going, but then you come out of the woods and you see the light of day, and it's hallelujah. You know you are close, and we know we have essentially just answered this integral. So we've gotten rid this sophomore's dream. We've gotten rid of this integral, right? Based on the pi function, we've replaced it with n factorial. So we have killed our n factorials, which leaves us with nothing more than the sum as n equals 0 to n equals infinity of 1 over n plus 1 to the n plus 1. But now, just to make this answer look a little nicer, I think you'll appreciate it. You can say it's the sum as n equals 1 to n equals infinity of n to the negative n. Oh, nice, isn't that? So, just to kind of conclude things, I'm going to just have to erase this here. We've said this, so we've just concluded that the sum as n goes from 1 to infinity of n to the negative n, we've said that that is the same thing as the integral from 0 to 1 of x to the negative x dx, which, if you're curious, is approximately equal to 1.291. And so here we have it, my friends. Oh, wow. A little bit of a lopsided box. But no matter, it is a beautiful result nonetheless. I mean, I think, hopefully, you just get the same sense of awe that I have, because the reason why it's named Sophomore's Dream is because it's something, this identity, right? And actually, just for kind of clean this up, I'll just make this box a little bit better. Right, so finish this integral 1, and then obviously we're going all the way. There we go. There we go. A little bit better. So we've said that Sophomore's Dream, which again, as I said, it's just something that seems too good to be true, because we said that the integral from 0 to 1 of x to the negative x dx equals the sum from n equals 1 to infinity of n to the negative n. I mean, it's this, this function raised to that function that's really nice, parallel, and then 0 to 1, 1 to infinity. And then, of course, that it equals something like 1.291, which is kind of interesting. But it's just absolutely amazing. I mean, I personally think this is one of the more fun proofs I've done just because it's so fun. And I really hope you've enjoyed this video, and I really hope you've enjoyed this proof and learned something. I mean, I think definitely the pi function is very interesting, and Taylor series. If you have not learned that already, I encourage you to learn more about that, and I'll put information in the description if you would like to learn more. And so, if you have any questions or comments, I'd love to hear them and answer your questions, and we can all share in the beauty of math and in the beauty of learning. And yeah, I mean, I think this is just one of the most fun proofs, because we are taking these very interesting and disparate components and ideas, right? I mean, the pi function. I mean, we're using a series, expression for a function inside of an integral. I mean, this kind of looks wacky. I mean, we have an integral, and then we have a sum inside of it. And then of course we can just beautifully, it just simplifies so beautifully because of the pi function. And just crossing that off just feels so nice. And I really think that this just so well exemplifies really a poetic symphony. We have clever substitution and summations and Taylor series and pi functions all coming together in this very harmonious and ultimately stunningly beautiful and satisfying answer. And this was really fun thinking about and proving for you, and I hope you feel the same. And I hope you have a wonderful day. I hope you have a wonderful rest of your math-tastic day.